The first question is very hard. I think there's easier questions later. I think there's easier questions at the back. That's the end of the test. I can't do any questions. Oh my gosh.
Hello, everyone. My name is Ken, and if you have ever been in that kind of situation before, then welcome to the second episode of our series called Calculus for Dumb Babies. In this series, I will try to teach you guys calculus in a way that is simple and easy to follow. So, whether you are just like a primary student who has interest in calculus, or maybe you are someone who have graduated but haven't really touched calculus in a while and wants to revisit some of the ideas, this series will be perfect for you. In this episode, we will explore the concept of what we call limits in calculus, continuing from the first episode, which if you haven't seen it, you can click on the eye on the top left or right hand corner or click the link in the description below. With that said, let's begin. Okay, so let's start off with the recap for the first episode of our series. So in the first episode, we looked at two separate problems that actually relates to the two fundamental idea in calculus. The first problem is the problem about the area of the circle. This was proposed by the Greek philosopher because they were studying like how to find the area of different shapes, like the square, the rectangle, the triangle, and all that. They were trying to find the area of the circle, and that gave rise to the idea of integration in calculus. The second problem is about the speed meter. Like when we drive a car, there's like the speed meter that we always look at when we want to know our speed. And that idea is actually relates to the fundamental idea of differentiation in calculus. Now, let's recap a bit for these two problems respectively, all right? Before we proceed. So, for the area of the circle, one of the Greek philosophers, which his name is Archimedes, actually came up with a very clever solution to actually find the area of a circle. So, what he did is he divided the circle into pizza slices. So, what I mean by that is he divided the circle into pizza slices like so, like this one here. This includes 8 slices, right? 1, 2, 3, 4, 5, 6, 7, 8. And what he noticed is that if he rearranged these kind of slices, he can rearrange it into a shape that looks kind of like a rectangle. And that's exactly what he did. So he rearranged the 8 slices into the shape in this thing right here. And he noticed that as he increased the number of slices, for instance, going from 8 slices to 16 slices, like this one here, going to 16, so basically this means that you just kind of separate in between, like this. When he separates into 16 slices, what he gets is a shape that looks even more like a rectangle. And then when you do 32 slices, which means slicing even more into the shape, he got that it looks even more like a rectangle. So by doing like infinitely many slices, we can get like a perfect rectangle that has the area equivalent to the circle and compute the area of the circle to be pi r squared. So this is like the first problem that we tackled last episode. And the idea of actually just cutting into like infinitely many small pieces and then summing up together, that is the idea of the integration that we talked about last episode. Now, for the speed meter problem, we noticed that the definition of speed is like the change in distance, right? Divided by the change in time. But how does your car display the speed like immediately? You have to have 2 points in time to determine the speed, but your car displays the speed like every instant. So we looked into like how your car did that, and it's actually performed a very clever trick of actually just moving very small in time. For example, moving like 0.1 hours in time and actually compute the speed out of that small interval. And that's how your car displays the speed at every moment, because it's actually just kind of like shift tiny bit and then compute the speed of that small interval. And that is like the core idea of what we call differentiation that we discussed last time. Okay, so with this two idea, in the last episode, I told you that in this one, I'm going to describe a tool that allows you to define these two processes mathematically. Let's just think for a minute on how to actually define both of these things. So for the problem of the area of the circle, what we did is we have infinitely many slices. And for the speed meter, what we do is we cut it into a very, 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 very small interval in time, and small that we can just kind of ignore it in the end. So I think like the most natural way to actually define this mathematically is to write something like this. Of course, we are making infinitely many slices, so why don't we just write slices equals infinity? I think that's maybe a valid solution. And since like the change in time is almost zero, like we can just ignore it anyway, why don't we just write change in time equals zero? I mean, that's the most natural solution if you ask me. But there's a problem with this solution. First of all, let's just discuss the area of the circle first. Having the number of slices to be infinity is not mathematically correct. Because really, infinity is just a concept, right? Infinity is a concept of like getting larger and larger and larger without any bound. If you have like a variable equals infinity, what does that even mean? It may seem like, okay, that variable is a lot, but even a very large number, maybe 10 to the 10, and that means 10 times 10, or maybe just 10 to 100, over 100 times. And that is not even infinity. Infinity is just so much. So we can't really write like a number equal infinity because that doesn't really make sense, right? There are actually two problems that arises in the case of determining the speed for the speed meter. The first problem is that it's literally just kind of wrong with the definition that we talk about, because speed is defined as the change in distance over a change in time. But if we just say that, okay, change in time is zero, then there's no change in time, right? And so that's just the definition to kind of break down. And that's really the reason why we invented the differentiation in the first place, right? And another reason is that if that time factor actually is zero, it's going to be divided by zero. And you may say, okay, what's the problem with that? The problem with that is that it is mathematically undefined. You can have like 0 divided by 1, that equals 0. But if you have 1 divided by 0, that is undefined. And the reason why it's undefined, because just ask it to yourself. Like, if we have a cake and we share it with 0 people, what does that even mean? Like, it doesn't really mean anything. And, there's some interpretation of this phenomenon. You can look it up on YouTube. But, just for the sake of it, I'm just going to say that it's going to be a problem in our definition of these two processes. All right? And so, how do we actually just define these? Because one option, like we can just use other symbols, like this is equal, right? But we also have something like approximately, greater, less than, or greater than equal to, less than equal to. So these are some of the mathematical language that we know of. But let's just start with the slices approximately infinity. What does that even mean? Or slice less than infinity. I mean, okay, but that doesn't tell you anything about the process we are trying to do, right? Because we are trying to cut the slice like so many that it's just kind of like close to infinity, but it's not exactly infinity because we can't really say it's equals to infinity. Because like we can't really use any of these. And similar thing for the change in time. You can't really use any of like change in time approximately zero. I mean, that could be valid, but it doesn't really explain anything we do. And so how do mathematicians allows us to actually define this rigorously? Well, this is the way they get around to it. Slices is not equal to infinity, but we can say that slices approaches infinity, right? Something like this. The number of slices actually approaching infinity is not equal to infinity, but is approaching infinity. You know what I mean? And we can say the same as changing time. It's not zero, but it's a value that approaches the point of zero. And that, my friends, is what we call limits. For example, if we have n slices, n being the number of slices, so I just write here, and n can be any number. For example, when we chop it into pizza slices, like 8 slices, then we can write, okay, n equals to 8. And when it's 16 slices, we can write n equals 16, 32, and so on. We can write this notation as something like this. Area of the circle equals to limit LIM, which is the abbreviation for a limit, and then we write the number that is approaching something in the bottom. So limit as n with the arrow, that means approaches infinity of whatever this is. And I'll discuss what this thing here in the blank more in the episode about integration. That's going to be the fourth episode that is coming in this series. But what I want you to know is that we can write this lim and arrow infinity or limits as n approaches infinity is literally just kind of summarizes the idea of that we cut into infinitely many slices and summarize in this compact notation. All right? It might look a bit scary, but that's like just kind of like the meaning that this notation actually stores, and I think that's really cool. For this one, on the other hand, we can say that speed equals to limit as, for example, if we make the step in time, like I'm just gonna call it h, that is just a number by the way, and that can equals to like 0.1 or anything that is small, right? That's like the small step on time that we just kind of analyzing. So we can say that limit of h approaches zero. We can write it as h arrow and then zero right here of whatever this is, which I think I showed you in the last episode how do we derive it. But for now, let's just kind of leave it as a blank, and then I'll talk about it more in like the episode about differentiation. All right, which is the next episode. So now we have established a compact notation for describing these two phenomena, like from chopping into infinitely many slices, we can use limit as n approaches infinity, n being the number of slices. And for speed, we can say that, okay, it's a limit as the step in time approaches zero, and that summarizes in this compact equation right here. And yeah, that's really the reason why limits is actually invented. If you look into most of the textbook about calculus, like from what I actually learned from my classroom and from my AP thing that I actually took last year, a lot of times, like when they introduce this limit, I don't really know like what is the reason of that we are studying this thing. But I think this is kind of like a clear illustration to you on why we have limits and why is this necessary is because we needed to define this kind of thing, this kind of process of thinking that of going to infinity or approaching something. So that's really the main job of limits. But since we have defined the limits, right, let's just look at a more general property of what limit can really do, and that's going to be the next slide. And so let's look at a more abstract case. So in the previous episode and like from before this, we actually looked into like a more kind of like practical example, right? The area of circle, we can really see it. And for like the speed, we can really just kind of visualize it in our daily life. But now let's look at some of the more abstract concept, which is really just kind of like in terms of graph. So by looking at this slide, you might be shocked to see that what is this thing right here? I mean, if you look at this graph, like this graph is actually very similar to what you see in this slide, right? But the only thing here is that what is this symbol in here? Well, this is what we call functions in mathematical terms. And really, it's just a more fancy way of actually writing what y is. The horizontal axis is actually called the x-axis. I label it here. And for the vertical axis, it is actually called y-axis. It's just a more compact way of writing y equals to x squared. And you may be wondering, like, why do we have to write it in such a weird notation? Well, because this notation actually has a lot of benefits when it comes to analyzing different graphs. For example, if you have to graph, if you're going to use like y equals to something, I don't know, and then this one use y equals to something like this, it might be okay in some cases, but in a lot of cases where we are analyzing like the graph, it may be a bit inconvenient. Sure, you can use like subscripts as y1 and this one as maybe y2, but it's not going to be that convenient in many cases. And another reason is that if you want to evaluate the y value at different points, for example, at this point x equals 3, if you are going to write using like the standard y notation, what are you going to write? You might write as like y at x equals 3 equals something like this, which I think is actually not that kind of convenient when you work with a lot of things. As a function, you can actually write something like this, f of 3. And that says that the function or the y value is evaluated at x equals 3. And if you're wondering why it's called function, it's because like you're taking input x and then you output something, and that something is actually y in this case. All right. I just also want to note that this value can be anything, right? I mean, it can be like t, for example. In a lot of cases in physics, you will see this as t for time or something like that. My question is, with the definition I've told you about limits so far, this thing is like the limit as x approaches the point 3, meaning that as x approaches this point, what is the value of the function at that point? For the limit, it's approaching, right? So basically, it's the value that as x get closer and closer to point 3, what does that value approach? And you can see that, okay, so for the point 3, right, f of 3, which is this thing right here, since this actually has the function of x squared, which just kind of like x times x itself, so basically the y value at this point is actually 3 squared, right, because we have x equals 3 and that equals to 9. And you can see that the graph here is actually approaching that point, right? So you can say that, okay, so limit of f of x as x approaches 3 is just 3 squared, right? That is equals to 9 and also equals to the value of the function at that point, which is f of 3. I want you to look at another example and I also want you to maybe think about it for yourself before I actually give the solution. So let's go. For the second function, it's really similar to the first function, right? Only thing that is off here is that x is not equal to 3. And what I mean by that is the function is defined at every point, right? So basically at every point you can compute the y value from the x value. The exception is like the point x equals 3, which I put large dot here, symbolizing that at this point there's no values of y you can compute for this graph. Alright, so this is a bit kind of exaggerated, but basically every point around 3 we can compute the value, but the exception is only at point x equals 3 exactly. With the definition of limit so far, what is the value of limit as x approaches 3 of this function right here? You can pause the video if you want to, but I was just going to give you 10 seconds, right? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, let's get our answer ready. You should be able to answer that this thing is equals to 9, which is the same we have last time, which is 3 squared. You might be asking, well, why is this value the same? Well, it's because that even though we don't have the value of x at point x equals 3, we don't have this thing right here. But it's actually just approaching the same point, right? The limits is what that value approaches, and this is actually approaching the same thing. So that is why the limit as x approaches 3 of fx is still equals to the same value. I want you to think that it's just explaining the process of approaching something, not equal to something, but approaching something. Just know that this is not equal to f of 3, right? Because f of 3 here is undefined in this case. Now, let's take a look at another example. This thing right here. Let's take a look at this. What does this even mean? This function actually has two parts. The first part is the below part, which actually has the equation of f of x equals to x squared, which is the same thing that we had. And you see, this function is actually just kind of like grows up, and there's a color at this point. This means that the lower part actually has f of 3 within it. Like this thing is actually belongs to the lower part. On the other hand, for the upper part, it actually goes onwards, and there's a blank here in x equals 3, and that means that for the upper part, there's no x equals 3. And so I wanted to ask you, what is the limit as x approaches 3 of this function right here? 3, 2, 1. Okay, so let's just think about it for a second. Limits is about approaching, right? But you see, if you look from the left side, it's actually approaching f of 3, right? So basically from the left side, it's actually approaching 3 squared, which is equal to 9, right? Because it's actually approaching this point, right? It goes to this point. Since this function has this equation of x squared, so basically this is actually approaching 3 squared, which is 9, alright? On the other hand, if you look at on the top, even though we don't have f3 defined for the top part, but you can see that it's actually approaching this value, right? And since this actually has this equation of x squared plus 5, we can say that it's approaching 3 squared plus 5, and that equals to 14, right? So what is the limit? Because it's actually approached different values. Like left side is approaching 9, from the right side is approaching 14. So what exactly is the value then? The answer is that it doesn't exist because we can't really find a value that this actually converges, right? Because if you go on the left, it goes to 9, but if you go on the right, it goes to 14, and it doesn't really converge to a single value, and that is why the limits doesn't exist. However, we can write something like this instead. Limit as x approaches 3 from the left, which in this case will denote as this tiny negative sign on top. All right. This means that it's coming from the left of fx. This is actually equals to 9, and it's this value right here. Similarly, since the right side is like the positive side, we can write the limit as x approaches 3 from the positive side, f of x that equals to 14, which is this value right here. All right, so the limit, the total limit, like the limit as this function approaches 3 doesn't exist. However, we can still compute the limit on the left side and on the right side, respectively, from visualizing the graph, right? Okay, so I think that's the overall concept of limits. It's just approaching. So if you understand what approaching means, I think limits shouldn't be too hard for you. Now, one of the benefits of having a limit, or one of the main purpose of limits, is it can be used to describe whether a graph is continuous or not. Let's think about a single line. So if you have like this line right here, how can you say that it's continuous? For example, I want to ask like, at this point, is the line continuous? At this point, right here. Well, first of all, I think the natural question is that for this point to be continuous, there should be this point, right? If you ask like, okay, is this space continuous? Of course not. There has to be a point at the point that we want to say whether it's continuous or not. So basically in the graph context, we can say that for a graph to be continuous, first of all, the value at that position, for example, at point equals to 3, then f of 3 must exist, right? So that's our first criteria. For the second criteria, if you have something like this, right, you cannot say it's continuous, right? Because it just kind of goes here and then jumps over here. And so we cannot really say that it's continuous. And so in order for the graph to be continuous, this side here has to approach the same value as this side, or in other words, the limits exist. So limits as x approaches 3 of f of x must exist. And the third criteria is that these two things must equal, right? Because if it's not equal, then it's going to be something like this. There's a blank here, and then there's this single dot going on top. So the values will kind of like go like normally, and it's just dump all the way here, and it goes to. So basically, these two things has to equal each other. So the limit must equal the function itself. And that are the three criteria that we can use to say whether like a line or a graph is continuous or not. Continuous meaning that there's no hole, there's no jump between it. So it's just kind of a smooth graph going in the XY plane. So this concept is a bit kind of abstract. By having a limit, you can define whether a function is continuous or not mathematically, and that's one benefit of having a limit. Another benefit is that it can allow us to describe the behavior of some graph, like for example, behavior of what we call asymptotes. There are two types of asymptotes. There are horizontal asymptotes and there are vertical asymptotes. You see, in this graph right here, right, you can see that the graph just kind of goes over, and then as x increases, the graph just kind of like approaches this line right here, right? Approaches like a single value. This line is what we call horizontal asymptotes. And it's basically like as x goes to like infinity, it's going to like approach this line. And so we can describe this behavior through limits. Limit as x approaches infinity. For this function here, this is actually equals to whatever this value is. For example, if I say that, okay, this value maybe is 2, this is equals to, all right? And similarly for as x approaches negative infinity meaning that it's this side, right? It's just infinity in the other side. Negative infinity of fx is going to approach this thing, and this is, for example, if this is 2, then this is going to be negative 2. And we can actually use limits to define this kind of behavior of graph, which if you don't have it, you can't really write anything like this compactly in terms of mathematical terms. And so by having this, it actually allows us to express this kind of thing more easily. Similarly, for the vertical asymptotes, it's just horizontal asymptote but flip upwards. So in this case, you can see that this line here is the vertical asymptote, right? You can see that limit as x approaches 0 of f of x doesn't really exist, right? Because on this side, it's actually approaching negative infinity, right? but this side is actually approaching infinity. And so since these two are actually different values, on the right is approaching infinity, but on the left is approaching negative infinity, so the limit doesn't exist. So we can use limits to actually describe this kind of behavior with graph, which is actually really cool. So there are much more things about limits. For example, in Calculus 1, you will learn how to compute limits of maybe like weird functions like trigonometric functions, which is like sine, cos, inverse trigonometric, like arctan, which is the example that I showed you in this slide here. You also learn about maybe like squeeze theorem, intermediate value theorem, L'Hopital's rule, and this actually read as L'Hopital's, right? Not El Hospital, because it's French. But anyway, what I want to say is that this video is just like the overview of the concept of limits and why do we even have this concept in the first place. But if you are going to study in this kind of course, there's still kind of a good amount of content that I didn't cover in this video right here. It's also require a lot of practice. For example, if you're going to have a midterm exam or final exam, you probably has to do more than just watch this video. So that's a bit kind of disclaimer I want to point out here. But I think by watching this video, if you understand so far, I think you're going to have a much easier time to comprehend the concept of limits and actually makes like other kind of content that is presented makes us more to you. And that's it for this episode. Thank you so much for watching. If you watched it far, don't forget to give me a like, subscribe, and also comments. I hope you have a nice day and see you next time in the third episode about differentiation. Bye bye!